Hello, everyone. So what I'm going to do today is, I should have finished this last time, but let's look at a web server, tiny web server, and let's try to use that to understand some of the basic concepts of the web, how we get information using our browser, how web servers work. So this is a web server that we provide you in this week's lab, and you have to hack it a little bit. And I cannot emphasize enough again and again that you have to do these exercises, both in lab 7, 8 was optional, sort of good if you did that, and this week's lab. We are not making you write network applications from scratch, but you should be able to look at the code, get a high-level view. I've been telling you that using the API is really important. And when the assignment, we'll release the assignment, this way there will be no surprises. Like you'll be on top of everything. And I've been telling again and again. So I've been doing my job, making sure that you guys really finish this week's lab 7, and you're able to write. And I'm going to take you through the 240 lines of code, and we have a working web server, really remarkable. And you will see the power of Linux, Unix once again. A lot of the things that we have discussed in previous lectures, previous weeks, will all come together in today's when we look at the code for the web server. So clients and server use this application level protocol, HTTP, and the World Wide Web, the way we serve the web content, the way the host, the clients and the servers communicate, it's really a protocol suite. It's not just one protocol. they build on top of each other. So IP Internet Protocol provides the unreliable service of packet delivery. It provides a naming scheme. It decides where to route information. And then TCP makes sure that the communication is connection oriented, reliable. And on top of that, HTTP allows us to, at the application level, to communicate with the web servers what kind of information we want and in what format we want it. This is application level because you can actually write the requests and you can actually understand the messages. They're exposed to you. And this processing happens in the application code. So TCP is hidden inside the kernel. You don't know what the operating system kernel is doing, which is okay. You don't want to be exposed to everything. But the web content is delivered using HTTP, and this is why application programmers need to know a little bit about that. So there are requests and there are responses. Clients, think of web client as a browser. They make requests for content, and then the web servers respond. And these requests, messages, and responses have a specific format. It's really very simple. And the content is shared using a format called MIME. This is basically associating with a bunch of raw binary data, a type. So you can convert it into, clients can convert it into a format that is, appropriate for displaying, for instance, images, plain text, and all that. So when web servers return content to the clients, they actually specify the MIME type. I was telling you that web servers don't just return static content. You can actually request the server to run a program and return the result of the execution of the program to you as a client. And this is called dynamic content. And static content is when you just ask for a file, image, web page, and all that. So when this communication takes place, here is a URL that the clients use to inform the server what they are looking for. So there's portion of the URL that specifies the IP address, the host name, and the port, and then the server uses the rest of the information to find the specific file the client is looking for. If you just say, this here is not the Linux root directory. This is the home directory where all the content is stored on the server side. So the server will go to the home directory and look for index.html. And if you don't specify this, if you just specify this or don't even specify this, the default is the server will look for home.html or index.html. It really depends on the specific website that is served by a server. So clients use this prefix to identify the host and port, and servers use this to identify what the client is looking for. And soon we will see that, so this is when you want static content. And soon we will see how we can request dynamic content. And some of the questions that you should think about in your head is, when we look for dynamic content, when we request dynamic content, how are we going to specify the parameters, arguments to the program that we want the server to run? How are we going to specify what program and all those things? So we do all of that using request on the client opens a connection and then sends a bunch of requests, which is basically just text messages. So web browser is nothing magic. It's under the hood. It's just sending a bunch of request messages using this specific format on this slide to the server. And the server responds with a specific formatted response in a specific way. So the request here, there's a method, there is a uniform resource identifier, and then the version. So this is a client. This is a client asking the server, I'm looking for something. I want you to do something for me. And so method could be the most basic method is get, the get request. Get me a page, right? What could be more simpler than that? What do you want from a server, right? Get me something, get me a page. Or you can post new content using post. You have all these other methods. Delete, you are worried about some information you placed on the web and you want the server to delete it. And hopefully the server will not use it for something else. Trace, post, all these methods. Get is the one that is most relevant to us in this week's lab and in the assignment. And then the uniform resource identifier is the /home.html, which tells the server what you are looking for. So URL is this complete, uniform resource locator is this complete thing, host name, port number, and the URI. URI is just a small part of the entire URL. So URI is just, home.html or whatever. And then the version is, the client is saying, look, I want can you be nice to me and, send me something that I understand, 1.0 or 1.1. We'll do a demo in a little bit where we'll actually send requests to a server somewhere just to annoy people. So, and then the responses come back. So here, so what I want to show you today is, so the web browser is doing all of that under the hood, but you can actually use Telnet, a very simple program that I introduced in the last lecture, to poke servers, to do the things that the browser is doing for you. So manually make these requests and try to understand these responses, try to interpret these responses, which the web browser is doing for you, which we don't see. So we want to demystify this magic of what the web browser is trying to do. So, and then responses come back in this format with the version number and the status code 404, 301, 200, and some message describing the error. And the response is a response line followed by 0 or more headers, possibly followed by content, with blank lines separating headers from content. So for blank line, historically, they use the carriage return and line feed. I don't know why they decided that, but this is what this convention is. And when you send requests, you also need to send a carriage and a line feed to end the line. Okay, we'll do that in a little bit with Telnet. So the response header, so there's a response line, and then the response header tells you certain things about the content you're about to receive. The type of content, the MIME format, the MIME type. Is it an image? Is it a web page? What is it? Is it a plain text? And the length of the content minus the header. So this content length tells you, the header tells you how big is what is the size of the content that the server is sending you. So there are also headers on the client side that are used to provide more information to the server. Okay, so I think I want to do it. We can talk about these things. This is very abstract. I want to run the Tiny server that we have given you in this week's lab and try to play with it a little bit and see if it works. So I want to unshare my screen. And what I want to share is my desktop. Okay, can the online students see my shell now? All right, great. All right. So here's our tiny web server. It's serving Godzilla.gif, Godzilla.jpg. There's a home.html, really simple, but you can hack it to make it something way more useful. Now, I'm going to make it a little bit. So first of all, let's try to understand how the web browsers send request messages whenever you type a URL in a web browser. What happens under the hood? Let me try to get Telnet to return me the Google web page. And let's cross our fingers. These things don't always work. So I'm going to use Telnet, which is a tool to probe servers. It lets you actually make the requests, headers, and everything, which the browser is doing for you once again. So I'm going to use Telnet. So in the lab, you will need to compile it. Here, I've already compiled it, and I tested the makefile and everything myself last couple of days ago. I think it should work on all platforms, but let's see. Okay, so I'm not going to run the Telnet, the tiny web server. I'm first going to show you what the web browsers are doing under the hood. So I'm going to say Telnet. I'm going to connect to this host name and port number 80. This is a well-known port that takes HTTP requests and serves web pages. So my connection is successful, first part done. And Telnet tells you how to get out of this. Getting out of these classical tools, command line tools, is not always easy. So for instance, if you start typing enter, if you start typing, back, I don't know. So you really have to type control and then a square bracket, and then you'll get this prompt, and then you quit. Okay, well, let's do this again. Okay, so I want to get a web page. So imagine you go to the web browser and you type a URL. So what will the browser do? It will create a request message, get homepage, right? Slash will be interpreted by the web server as homepage, right? And let's ask Google to return us something in this format. Now I want to press enter. And when I press enter, Telnet will start a new line, and Telnet will insert carriage return and line feed for me. So you don't see that here, but Telnet has already done that. Now it's important because when you hack web servers and when you do the labs, you might need to do this in your C code manually. Telnet is already doing it for me. So get me the home page and send me, and use this format if possible for the response. And so I'm going to use a header here. So this is the request message or request alone. And I'm just going to use a header to give, sometimes it's useful to give more information to web clients. So I'm going to say, use this host. Okay. Maybe it will work even without it, but I'm just going to say that. So if I say press enter, nothing happens. I need to press enter again. And this is the Telnet. So this is the protocols convention that headers should be followed by a blank line. So when I have a blank line, I don't want to go through this entire thing, but it looks like a web page, right? So web browsers are no mystery. Under the hood, they are doing this. So what is returned is HTML, hypertext markup language. And if I have a web browser, if I copy paste all this, if I have all the time in the world, if I don't have to teach, do research, if I get this, I can open a web browser, I can dump all the code, and I can see that. I can see that it will look like Google, right? And all the hyperlinks here, the web browser will look at the hyperlink and make another request. Make another request, right? But here, I'm not doing that. I don't have that time. I don't want to do that. And So the web browser will do a lot more. It will go inside the hyperlinks and fetch all those pages, get requests for all those hyperlinks, right? But here I'm just showing you that. So this is so once again, all this is HTML. And this is all tags and everything. This is formatting information for the web browser. Web browser will interpret it and display it. This is the markup language. And this here is the HTTP protocol. This is the protocol used for text messaging between clients and servers. Like this, the same way we use WhatsApp, but we don't have any rules, right? We say whatever we want. But clients and server have specific rules. You can't just say, anything you want. You have to follow a language, a protocol. So the distinction between HTTP and HTML should be very clear to you. So I can go and tried a few things yesterday, and some of them actually worked. So let's say, so we'll go to CMU, and the book's authors page is, let's say, so go to home page, so home directory, then go to, and they're set up. And if I can, okay, something went wrong. Second try. Maybe I guess I did not have the all right, bad request. It's still a bad request. So something is wrong somewhere. Anyway, you get the idea, but I'm just trying to be. You don't get a lot of shots at this. All right, so you get something. If you try hard enough, you can get something. So that's why you want to use a browser. You don't want to, but in the labs, you should use this for debugging and everything. This is a tool for debugging, for probing servers and seeing people who write web browsers actually use this. We will let you use it in the lab as well. So I don't know if we, so if we look at the response here, what is actually returned by the, so Telnet is saying it's able to connect to this IP address. So this IP address is resolved from this host name in English, and this is done by Telnet using DNS service and whatnot. It's connected to this server, and I wrote this, and then at some point it said, I don't know. Okay, it's still not found, whatever. So if we go here with the Google one that actually worked, 200, okay. So this is the response. So the server is saying, this is a type, this is a status message, and the description is 200 means okay, right? So things worked. Date, expires, content, content type, HTML page, some more information, and a bunch of other things. Okay. So this is an example of something that actually worked. This is a friend's page, and so what I want to show you is the length of the. So this is again all the HTML. So somewhere there should be content length here. So the header is telling you what you're about to receive has a length of blah, this many bytes that you're about to receive. Okay. Okay. So I want to look at the tiny web server. Right. So you want to make sure that you have a big enough. So these are all the things from malloc and all those problems that you have anywhere in computer systems, right? Not just specific to this. So I was saying that Tiny, that this week's lab is about partly the Echo client server and Tiny. If I look at the number of lines of code, it's really 240 lines of code. I mean, this is something you can do it in 2 hours or something. But I will take you through the what this code is doing. Let's just run it first. So I'm going to run the Tiny server, and I just want to pick a port for running it. And the kernel will pick the IP address of the local host by default. I don't have to specify the. So let me run this server on port 9000. Okay. So now this server, let's say I have a new startup idea and I'm running my own server. And so this server is running, and someone wants to get the content that I have. So let me go to a different terminal. And how should we do this? Let me use telnet. So localhost 9000. So the server is running at 9000, and I'm using telnet to probe the server and to get the web page. So I'm just going to make a request. So I will soon do it in the browser as well. But let me first do it by hand manually. So give me the web page, the home page, and I'm just going to say this is the version number, and let's be super careful and just provide the local host. And if I do this, then I get this HTML back from the server. And if I go to the server reports that the connection did succeed, and it created the response headers, 200 OK, server connection, all these things, and it returns the HTML. So the first thing you should do when you start the lab is make sure that on your machine, when you start the Tiny server on a specific port, and then you probe it using by composing a HTTP message request, it actually works. Now, I can do the same. So if I go to the web browser and I say localhost 9000, it will actually communicate with the web server that I'm running, and it will return the home page. This is a home page. Okay. So the browser is doing internally, creating all these request messages and all that. And we can do the same using telnet. We can compose it ourselves. We can turn ourselves into a web browser. And in this part of the course, we want you to become comfortable with how web content is delivered, how connections are made by giving you an API that is as comfortable as possible for you. But you have to attack the lab, and you have to show some initiative. Okay, so what about dynamic content? So this is all static content. Okay, all good, you know. Okay, so here, from the web browser, the Tiny server is actually able to tell us that the response, the connection was made to Google Chrome, Macintosh, Intel, whatever. It has all the information. So we know that it's working. So make sure that it's working for you as well, and start playing with Lab 9. Now, what about dynamic content? So this is all good. You can ask the server for static content. The sort of the it's not a protocol standard used for dynamic content delivery historically is called CGI, Common Gateway Interface, if I'm correct. And it tells us how to compose requests for delivery of dynamic content. So the web server is running a very interesting application that adds two numbers, okay? And we are going to use this service add.com to add two numbers. So we are going to ask the server, hey, execute this program for us, add the program, the wonderful program that you have, and send us the outcome, okay? So how do we do that? So I'm going to run telnet again. So my server is still running at port 9000 on my local host, on my local machine. So in this course, we do everything with localhost. And then when you do networking, you will do more advanced stuff. So I'm saying 9000. So telnet will make a connection. And so I'm going to say, get me the output of a program called adder, which I know is running on the web server. The web server I know has that program. So I'm going to say, so by convention, historically, all the dynamic, all the executables are stored in a special directory called CGI minus CGI dash bin. And whenever the server sees CGI somewhere in the URI, it knows that the client is looking for dynamic information, okay? And then it goes from, we will look at the code in a little bit. So the server then knows that this is not a request for static content. This is a request for dynamic content. And then it tries to figure out where are the parameters that I need to run adder, like what two numbers do I need to add, right? And those things are specified by the CGI standard. The CGI standard says, and don't ask me why, that you should specify the executable that you want the server to run, followed by a question mark, followed by the first argument. What numbers do we want to add? If we're using this service, let's add some interesting numbers. All right, question mark after the executable name, the first argument to the program that you want to run, and ampersand the second argument. Now, while inspecting websites, web browser, URLs, you might have noticed these things, ampersands and question marks and all that. This is what's happened. This is why. And today they have very interesting Ajax and JavaScript and all that. This is the old way of doing it, but it's still useful. So I'm saying I'm a client, and I'm asking the server, run the executable adder and add the two numbers 101 and 890. And this is the format that I'm using for question mark and then ampersand. The two arguments are separated by ampersand, and question mark separates the executable name and the arguments. And if I do this, and if I then create a header, just to be safe, and press enter, nothing happens. If I press enter again, okay, still nothing happens. So that's the problem with these things. Maybe you don't have the executable compiled in CGI bin. So this is CGI bin folder. Well, the executable is compiled. Well, so let me go back now. So I'm running it on port 9000. I'm going to say, Something must have been wrong. All right, this works. Well, whatever works. So I get a response back, 200, okay. The server says, I was able to find the either binary, you're looking for the correct service, we are ad.com. And thank you for providing the two arguments, and here's the result. The answer is 90 plus 78 equals 168. Thank you for visiting. Okay, the connection closed. So this is how we serve dynamic content. Now you could have a very fancy idea where, and this is already happening. I mean, most web pages today, when you request something on the web, they don't actually return you static content. They look at your cookies, they look at your message, they look at what you're searching for, and then they do some machine learning and who are your friends, who are you interested in, and then they return you, something that is going to spin your specific head. And this is so we can now see, we will now go inside the tiny web browser and we will look at the code. So we have a basic understanding of how to run these things. Okay, one more thing. I can do this in the web browser just to double check. So I can say in the web browser, let's say if this works, CGI bin add a 10% 89. All right, welcome to ad.com and blah. So nothing special in web browsers. You can write a web browser after this course. Okay, so I want to make you feel comfortable with the code because this is really important for assignment 2. So before we go back to the slides and do more things, let me take you through the code. So as I said, 240 lines of code, not a lot of work. But a working browser that is going to teach you a lot of things about how these things work and how the web works. So in the main program, in the main function, you have the listening descriptor and the connected descriptor. By now, you should be very clear in your head about the distinction between the listening descriptor and the connected descriptor. And we did that in the last lecture. So the server opens a listening descriptor on which it receives requests, connection requests from a lot of different clients. Server is an forever running thing. So you can see that, so the formatting here, unfortunately, is not very good. So I'm sharing the screen, right? So I can actually go to a better formatted. Oh my God, this is sensitive. Let's not do that. This is all your marking information, and I don't want to bring up something that puts me in a lot of trouble. So the formatting here is not good, but let's look at it. So this is the while one loop that the server is running. So go through these things, this sort of code that is kind of needed, but it really bothers you sometimes when you have to do these things. So it's running in a while one loop. It opens a listening descriptor, one listening descriptor for the lifetime of the server. It's just going to use one listening descriptor. And then clients come in, and so it blocks in the accept function. In the accept function, it blocks. Okay. When a client comes in, when a client calls the phone on the phone, the server, picks up the phone and gets to work, start talking. Here, it's just trying to print the information about the client. So this is the data structure that has a client address, the IP address and the port number of the client. This is part of the TCP protocol. The servers actually receive information from the client. If they don't, the things will not work. You need to know who's calling you, right? And then the server performs one transaction and goes back in the while loop, and in accept blocks again. So block, and when someone calls you, pick up the receiver, do this transaction, which is like a communication, and go back to the while loop again. And this close is important because you want to close the descriptor. By now, you should know that All of these things that we are looking at, virtual memory, descriptors, and all that, the kernel is maintaining special data structures to do bookkeeping about all these things that we're not exposed to that bookkeeping, but there are structures, linked lists, tables inside the kernel, and we don't want to create memory leaks. So we want to close things when we don't need them. Okay, so we want to close this descriptor before returning, and do it is doing this serving static or dynamic content. So really write your code like this, right? So this loop, the server, we could have written it so the server was doing everything in this loop, but no, we didn't do that. We used good abstraction. Okay, let's go to do it and see what is going on there. So if I go to do it, all right, so this is Vim bindings interfering with the, so Vim is the editor that I use. Okay, so do it is right here. So first of all, it's trying to figure out if it's static or dynamic content. So it has this buffer max line, as someone was saying, if someone types a request message or something, or there's a response that is bigger than the max line, then we'll have to handle this case. So it's using the robust IO package to scan. So what is it doing here? So this buffer buff is, so this is, it's reading the, so do it is past the connected file descriptor. So it's doing a read. It's not doing a read request. So here are these comments to make it easy for you. So this is a read request. It's trying to read, it will block in the read. And when the client types get / blah HTTP 1.0, it will get that in this buffer. And now it's trying to interpret that. So you will see a lot of scanf in this code. Scanf is reading the buffer and it's copying 3 strings in method, URI, and version respectively. So scanf is used for reading. Scan means scan, scanner, right? You're scanning. And the other function is the sprintf, which writes to a buffer. So this is formatted read. Scanf is a formatted read. It's reading the contents of the buffer. What is in the buffer? We don't know what is in the buffer. I didn't show that. I should have done that. But you could have bad requests. I could just type, I could just ask the server, stand up, not get or post, sit down. And these are things the server does not do, right? So we don't know what's in the buffer. So it's trying to tease apart the buffer contents into method, URI, and version. And then it does a compare, because we want to be easy to you. In 2010, we don't want you to go beyond get. Get is the only thing you do. Post, writes, delete, all those things are very complicated. It's doing a compare with get, and if the operation is not get, if the method is not get, it's basically returning. So all we want you to worry about in this course is get, okay? And this is what this code is doing. And then it's reading the headers. Remember, I was typing the request, and then I was typing the headers, host name, whatever you call, dot, colon, whatever, host name, all that. So now it's doing another read. It's reading the headers, and this is a different function. So I don't want to go to that function right now. And then it's figuring out, is a URI, uniform resource identifier. Okay. With web, there are many acronyms. And so forgive me if I use the, I don't remember the right one. I think this is what it is. So it's static. So remember I told you that if there is a CGI in the URI, then we know that the client is looking for dynamic content. So here it's using the parse URI function to figure out what the client is looking for. And inside this function, it must be scanning the URI and looking for CGI. And if there's no CGI, we know it's a static content. And then it handles the error. So this is all very bad formatting, unfortunately. And okay, if it's static, And it's a regular file. So it's doing some checks on the file. It just goes to serve static. And if we go to serve static in a little bit, we will see. Let's go to serve static. So serve static is basically, so here we have serve static. It's taking the file name, file size, the file descriptor, and then it's using a function get file type to get the file type. So this is the MIME format. This is the MIME type. Is it a plain text? Is it HTML? Is it a GIF? Is it a JPEG? Whatever. So get file type gets the file type. And then you see a bunch of writes. These are sprintf. So what it's trying to do, remember we saw that before it sends the web page, it actually sends a response. And that response has a specific format, 200, okay, HTTP 1.0, blah, blah. So it's using sprintf to create these responses. And you have to be very careful with sprintf, scanf, pointers, all that. If you mess up an argument, if you forget something, you will see the error somewhere else, 100%. You will say that, oh, the operating system is doing something wrong, or malloc is doing this. It's very hard to debug these things. Okay, so we specify the format here. So in buffer, so I'm creating this response in one big buffer, right? So first I write in this buffer a string, and the string is followed by a carriage return and a line feed, because that's the convention for HTTP. And then I write to the buffer, %s is telling sprintf that put a string here. This is the position for a string, and the string is stored in the first argument here, buff. So I create a buffer, I put something in the buffer, and then this is really clever. Then I specify the buffer here and the format of the buffer here. So this sprintf will write to buffer, buf here, whatever is already in the buffer, and append. So this is an append operation. All this is doing an append. It's taking the buffer and appending more things to it. And it's using sprintf for that. So you specify the format. This is a format key, and the contents. Okay, so this is how you use printf, scanf, these things. So it's creating all this response header, and then it's writing. So this is robust IO write, which I've been telling you that once you have a file descriptor, everything in Unix is a file. Most things are files. And once you get a descriptor, you really don't care what the underlying resource is. Is it a disk? Is it a storage device? Is it a network or whatever? You just use the file descriptor and use the read-write API, and the kernel will take care of it. Whether it's a network, it's storage, all of this is happening there's a switch inside the kernel that decides which way to go. If it's a network, go to the network subsystem. If there's a storage, go to the storage subsystem. And you will study that in operating system. So it's doing a write on that file descriptor, and a write on the file descriptor is sending a message. Read on a file descriptor is receiving a message. So it's doing a write, and then it's printing out response headers and all that. And so this is all the response message. This is all the response message, the content type and everything, and any header. So this is a response, send response. I don't know what they call headers and what they call message. There is a distinction, but anyway, let's just call it everything header. Response headers, whatever. Right, so all this is response headers. We haven't sent the actual content yet. We are in serve static. So here, it's now the server, after sending the response header, it's opening the file that the client is looking for. And it's using mmap, which is what everyone should do. No need to use explicit. You might have noticed if you've done lab 8 that page faulting mmap is faster than explicit read-write system calls. So it's doing this mmap, memory map file IO to open the file. And then really careful here, it's closing that. Once you map the file in the virtual address space, you don't need the file descriptor anymore. So close it. Good practice. So if you write C code and follow good practices, there is no reason your code, is safe and not bugged. But no, it's hard to do that, get that right. But it's good to follow good practice. So it's closing the file descriptor because once you have mmap, you don't need that anymore. And then it's doing a write, and this write is on the file descriptor that is provided to the serve static function. And this file descriptor is a client file descriptor. This is going on the network. And what is it writing? It's writing srcp, which is a pointer to the file that the client is looking for. So source P is a pointer returned by mmap. Mmap is memory mapping the file that is stored on disk on the server side into the virtual address space in the server's virtual address space. Once it's in the server's virtual address space, it is writing on the file descriptor of the client, the file. So it's basically copying the file from its virtual address space into the world outside over the network. And then it's doing an nmap, safe practice. You don't want to waste virtual address space. You unmap the mapping that you created. So I can say that it's okay to say that all of this 4-5 lines is a mem copy. It's not a mem copy. It's copying from memory to the world outside. You have the file stored on disk, map it into your virtual address space, write it out on the file descriptor, let the kernel takes care of where that write is going. Let the kernel figure out, is it a network or a storage, whatever, and it's a network. And that's it. That's a web server. That's already serving static content. It's really not that hard. Get file type. So you don't have to, unless necessary. There's a lot of code. Like, don't sit down and start looking at every line. Oh, yeah, I don't understand this. Move on and just get the basic idea. There's a lot of code here that maybe you don't need to know. You can just have a high-level view of what it's doing. Casting and all those things. So the idea is to be able to hack this thing, to be able to add new functionality. The idea is not that to learn it by heart, and we're not going to ask you write line number 24 in Tiny without looking at the code. It's not going to be that. So let's quickly look at how we serve dynamic content. And then we can go back to the slides. I just want to do, I really hate this when the casting is no problem. So this is a little bit tricky. And so when we serve static, we saw that the robust IO, the IO API will be useful. And when you serve dynamic content, the process, the knowledge that lectures, I don't know, week 4, process and signal handlers, that will be useful. So this is a good way to revise all the course content. So what it's doing here, once again, you get the file descriptor, the file the client is looking for, and the arguments that the client has given you to run the executable. So once again, you're creating the response message, you're writing it out to the server. Hey, I'm the Tiny web server. This is once again a write to the outside world, the file descriptor. And then the server is forking a child process to run the executable. Now, this will really be, well, first of all, this is CGI standard. This is part of the CGI standard. So to run an adder, to add 2 numbers, to fork a new process to add 2 numbers is really not very efficient. But this is a CGI standard, and this will really become clear in the next lecture when we move to concurrency, why this is important. Imagine instead of adder, there was a program called, I don't know, deep neural network or something that takes 2 days to run. So the server will be held up for 2 days, and no other client will be able to connect to the server. So by forking a child and letting the kernel do the concurrency, run the parent and the child concurrently in parallel, the server can take other requests while the child is still doing the work, especially on today's multi-core processes. So this is a way to get some parallelism and to not let the server get held up by one client. Okay, so we fork a child process, and then the way they pass the arguments to the child process is really not very pretty. You set an environment variable. So here, the environment variable is query string. You set the environment variable to CGI args, and this is how the child will then read the query string environment variable to deconstruct the arguments. If you remember dup2, which I did do in the storage lectures. So what dup2 does, so at this point, forking the child, what is it doing here? So everything the child will print will go to standard output by default. Where do we want the child to send the information? Where do we want the child to send the result of the add operation? To the client. So dup2 function copies the file descriptor, the first argument, to the second argument. So it will copy FD into standard out. And if you recall those lectures, the way the kernel manages these data structures, once you call dup2 like this, instead of the output going to standard out, it will go to FD. So FD will become standard out. Sorry, other way around. Standard out will become FD. Okay. And when this happens, all the output will go to the over the network instead of going to the standard.
Would like standard out all of the three, like name to be one?
Yeah, it's one. It's a one integer. And so, and that integer is used to index into a table which has the data structures and information where to print, how to print, and dup2 will sort of hijack std out and make that appear as FD. So instead of everything going to standard out, it will start going to FD. And the kernel will internally take care of how to do that. And this is what dup2 does. It's a IO redirection mechanism. So we looked at IO redirection, where you use the greater than operator to send output to a file instead of sending it to standard out screen. And then exec VE, which you must recall and must familiarize yourself again. It's here. It's your good old friend from lab, I don't know, 4 or something. And then so after fork, you use exec. And exec sort of subsumes the virtual address space of the, we have all this discussion in those lectures, how it works, and it never returns. And the adder executable will actually run in the context of the child process. So parent process will go back. Actually, here, the way they have written it, I think the parent process is actually waiting for reaping the child. But you could change this to make it concurrent, which we'll do in next week. Next week lab, next week lectures, will make this concurrent. So here, I think the parent is actually waiting for the child to finish, which really is not concurrent. Concurrent will be when the parent returns back to the while loop and accepts a new connection while the child is doing the addition. And this way you can have thousands of clients. One server can serve thousands of clients by forking new children to run the executables or serve the static content and accepting new clients. And sometimes you can create a lot of new connections. If you want to perform a denial of service attack. So this is how they do this. They make the server open so many file descriptors that the kernel just runs out of, it goes crazy, right? So this is how you do these kind of things. So once you learn all this, you can actually annoy others with these kind of attacks and all that. That's pretty much it. There isn't really much in this server. Parse a URI here, you're using standard library functions, str. I don't remember what it does, but it seems like if you eyeball this code, it seems like they're looking for CGI. And once they find CGI, they're actually, right. So they're trying to do a bunch of things here, which you should go in this only if necessary. I'm not asking you to, go in the code and just, every line, you don't have to, if you know what the function is doing. Okay, that's it. That's a web server. So the other thing I want to do is, so let's see how much slides do we have, and what are we going to do. So we have client and server, and imagine you have some other far executable, unfortunately written in Perl, but I'm going to show you, there's nothing, it's just an example, environment.perl, and the server pokes a child, runs the Perl code, and then returns the content to the client. And how does the client pass arguments? I think we covered these issues. These issues are addressed by the common gateway interface. Is it interface? Yes. The children are written according to the CGI spec. They are often called CGI programs. This is good to know. CGI is the original standard for generating dynamic content, has been replaced by serverless modules, but here we are using it to show you how these things actually work at the very bottom. Right, so this is something, if you ever forget what the ampersand means and what the question mark means, you can come to this slide. And so sometimes spaces are not permitted in the CGI standard. So they use the %20 to replace that. And that's why sometimes if you look at the browser URL, you see these ampersands, question marks, and all these things, percentage. I don't know if there's something here that we haven't covered. Serving dynamic content. We looked at the request and the messages. There's more information here, and actually we're done. Okay. Okay, good. So I'm gonna stop it. So this is all the networking part. Okay. Let me give you a heads up about assignment 2. So what you will be doing is writing a web proxy. So done with this. So what we have seen is actually a sequential server. It serves one request before going to the serving the second request. Okay. So it's not a concurrent server. At least this is from what we look at the code. So I've shown you how to use telnet. So telnet will be really useful for you from now on, and for assignment 2 to debug. When you write your code, you don't want to go to web browser all the time, and you don't know what's going on internally. You actually want to write, create requests and interpret responses using a command line tool. It's really like SSH, but it lacks the security features, and it's used to probe web servers. Curl is another tool, URL transfer library. It's a little bit high level than telnet, so you don't actually have to create HTTP requests yourself. It actually takes care of a lot of things for you. So it's below the web browser in terms of abstraction, but it's higher than telnet, but more closer to telnet. It actually builds the HTTP request for you. I'll show you in a little bit how it does that. And it can also be used to generate proxy requests. A web proxy is just a server that acts on behalf of a web server. So there may be a Google web server in the Bay Area, so that's really far away. So they might have placed a proxy in Sydney, Melbourne, I don't know where, because that is geographically closer to us, and then the proxy will communicate with the server in the Bay Area. So it's an intermediary that mediate between the client and the remote server. Proxies can actually cache pages and content. So when a proxy acting on behalf of the server doesn't have something, it can actually bring that information from the server, and it can cache it locally. When I say cache, you know what I mean. We have done caches. But this is a software cache now. The server has, the proxy creates, I'm going to say it in a very basic way. Let's say it does a huge malloc. And in that malloc space, whenever it gets a request from the client, if it doesn't have the page, so the online students don't see me. I don't know why I'm doing these visuals, but it gets it from the server and it stores it locally. So the next time the client make the request to the server, the cache has a local copy. So there are two benefits of proxies. They are geographically closer, they are strategically located. So the request can actually go first to the proxy and then to the server, and they actually cache content on behalf of the server. So what you're going to write is a web proxy that is concurrent, and it has a cache. It's a caching proxy. Proxies can still work without a cache, but we want you to write a cache. And don't be afraid from cache, it's just a malloc per client. For each client, you do a malloc, and many clients will communicate with the proxy at one time. And so you will need to do some concurrency tricks that I will teach you in the next lecture, next week. Actually, next lecture. So a single HTML page has tens, and this is the beauty of web content, that there are hyperlinks that point to other web pages. So when a web browser gets a response from the server, it actually scans all the hyperlinks and it makes a number of other requests. I wasn't doing that here. I was getting google.com and then just not doing anything. If I had more time, I would scan whatever is returned by the server and try to fill all the hyperlinks. But I am not a web browser, so I didn't do it. And that's where concurrent servers are really interesting, because you don't want to get one file at a time from a server. You want to get a number of files at the same time. So this is CMU's page, and you can see that there's a lot of hyperlinks. Most clients have some kind of a web, I don't know what they call it. This is Safari, I think. They call it, that actually shows you the transfers that are taking place when you're, I don't know what they call it, a portal or a logging something. So here we can see that we have a sequential proxy, and there's a bunch of requests at the top. And only when those requests arrive, we have requests at the bottom that are sent to the server. So this is a sequential proxy. Everything is happening sequentially, one after the other. And we can speed it up. All right, so how is this concurrent and this sequential? So if you look at the times, 11, 13, 21, 11, 11, 18. So if you look at the times, so here the top file arrives after 11 milliseconds, and 30 milliseconds, there is a second request, 21, 40, 40, 55. And here, 11, 18, 17, 26, 20. So all of these files, are actually, all of these requests are actually is being resolved in parallel, and all these requests are being resolved in parallel. When we get to concurrency, you'll actually get a more clear picture of, so concurrent proxy. So the code that we saw in the tiny web server will fork, the parent actually reaps the child and only then goes back. What we want to do is, without waiting for the child, we want to go back and make a new request, make a new request, make a new request. And somehow this shows that there is things are happening concurrently, and I'm not going to try and demystify what is there.
I think the purple is actually for you.
Right. So let's see this. So this one is after that, and right. Okay. Okay, it's just so networking basics. So all this will be part of the assignment spec or lab spec. Proxy, I will do a demo of the proxy. I do have a very basic proxy written. So cache, recall that you need an eviction policy. Once you have a large number of clients and you run out of space in the cache, you need a good replacement algorithm. And here, we are not going to impose that you write the world's best eviction policy and replacement algorithm, anything that works. And just, I don't know what the tutors have on their side. I hope it's not a random eviction policy. I think it's somewhere, it mimics a LRU, but there is a spec that will explain exactly what we want you to do. Least recently used LRU, if you recall, is you evict. When you are run out of space in the cache, you evict. When you want to make space for someone else, you evict the stuff that is the least recently used. So caches use this prediction that something that is recently used will be used again. So something that is not used recently, that was used far into the past, just throw it away. So you will need to do something like that. We'll have you write a multi-threaded cache. So you will have to cache content from multiple clients, but when you cache the contents, this will be a multi-threaded cache. So multiple clients will need to write to it, and you can imagine the issues that will arise. And we will teach you next week how to do locking, how to write safe concurrent applications that don't destroy the integrity of the data structures when multiple writes are taking place at the same time, or when multiple writers are in the queue to write something. So 2 threads writing to the same cache block, you will need to take care of that in your multi-threaded proxy. Okay, so here's a proxy, how it looks like. So we have the client at the very left, And the server at the very right, they have their own socket addresses, IP port pairs, and we have the proxy in the middle. Proxies are kind of special. They act both as a client and a server. So the proxy, from the perspective of the client at the very left, is a server, right? The client connects to the proxy on a specific address. And if the proxy does not have the page cached locally, it is going to send the request to the server. So for the server, from the server's perspective, proxy is a client. So you will write this proxy, and we will give you templates, and we'll try to make it as easy as we can, but you will have to do some. By some, I mean some, right? We'll see. So this is a high-level picture of proxy. So you will need to start with a sequential proxy, make it concurrent, and then add caching. So this is what you will do in assignment 2. And so all the APIs that I've been telling you and we've been discussing, Open Client FD, Open Listen FD, it's okay if you don't go inside the code and look at what's happening. You must be able to use it, because you're going to write a full-fledged application. So you need to know how to make this, use this API that is in cs.app.h and cs.app.c. Maybe write a simple client-server application. Maybe hack Echo client-server to do something interesting. Do the exercises that are in this week's lab, and that will make you comfortable with how this communication is set up, how the connection is set up. So you can write something like this. So you will need, I think, you will need, unless they are providing boilerplate for printing and scanning headers, you will need to use scanf, which is used for reading. And I cannot use my iPad for some reason, but I cannot annotate. But you see that this is formatted read. So you're specifying the buffer as the first argument from which to read, and then you're specifying the format that you want to read. And then the arguments at the very right are where you want to put this information. So it's almost like tokenizing what is in the buffer and putting those tokens in those arguments at the very right, ... And how do you want to tokenize it? That information is part of the format key. %s, %s, %d. I want a string, and an integer. And then it will put that. scanf will do it for you. So here's an example. Buffer 213 is awesome. This should be 2310. Anyway, so we have this in the buffer. And so what I'm saying to scanf, take this buffer, and the format string is %d, %s, %s. I want an integer and 2 strings out of this buffer. And scanf will store the integer in course and the 2 strings in str1 and str2. And the result is course will have 213, string 1 will have is, string 2 will have awesome, and return will have 3. Now you will need to use scanf and sprintf because you want to create request headers, you want to create response headers, so you will need to do these things. Sprintf, here's an example. You take so it's print, you're writing, it's printing. You are giving it a buffer. If you look at the bottom somewhere, you are giving it a buffer, sprintf, and you're saying, put in this buffer, write to this buffer, the word string, parenthesis open, and then you're specifying the format. And the arguments at the very right are specifying the variables that those formats refer to. So learn to use sprintf, scanf, either by looking at the tiny web server or by writing your own applications. You are going to become masters of delivering web content. And this is how web content is delivered. There is really no magic. This is, hopefully they're not writing web applications in C, but we are. All right, so there's a lot of other functions that will really come handy. String compare, string whatever, str, strlen. I'll let you Google that, all that. Okay, so one last demo of the proxy. And then we are done. So because I've been running a proxy, you know that I have it on my machine, so I don't want to get attacked by someone, steal my laptop. All right. So I want to share my desktop. And what I'm going to do is I just want to quickly do a proxy demo. All right, so I want to run my server here. Okay, server is running, doesn't print anything. We should have it print something. So now what I'm going to do is I'm going to start a proxy. And where is my proxy? So I want to start my proxy at a different port because my server is running on 9000 and I want to start my proxy on a separate port. So the proxy, I want to make the proxy communicate with the server. And I want to communicate to the proxy. I don't want to talk to the server. I don't like the server. Okay, so let me do this with curl, and I let you do it with, well, first of all, curl, I told you, is a, so remember with telnet, I had to create the request messages. Curl can just do it itself. Curl is a little bit higher level than telnet. So you don't need to create request messages. It has built in, like it understands that if someone is typing www.google.com, they must be looking for a web page, right? Whatever. You read them. Oh, and very important, always, we won't be able to write an assignment spec with everything. So man will be your friend. Man telnet, manual page, telnet, will tell you everything about telnet on your platform. And man curl, okay, so I want to communicate to the proxy and let the proxy handle the request. I don't want to talk to the server. So verbose minus I have to cheat because at the end of I forgot everything. So I have proxy. So my proxy is running at localhost port number 9001. And the proxy doesn't know where to go. So I have to tell it where to go. And I want home.html. Okay, so I'm telling curl, use a proxy 9001, and the web page that I'm looking for is localhost 9000 home.html. Okay, so this is a web server. This is tiny web server that serves ad facility and a Godzilla image. Okay. And this is my proxy that is running on 9001. And if I do this, it shows that it works. So I do get the response back. But now how do we know that there's something happened, a transaction took place between the proxy and the web server, right? Because unfortunately, I don't think the proxy prints anything. Okay, the way they have written it, then the proxy is not printing anything. So if I go to the tiny web server, it's saying accepted connection from localhost blah, and user agent was that, close, response errors. All right. Okay, so curl, okay, we can look at the output here to understand that it actually worked. So it's saying I'm trying 9001, and a connection is made to 9001. Okay, a connection is made to the proxy. Okay, and And after the connection is made to the proxy, curl is telling us that I created this request message and send it to the host, localhost 9000. Okay, so this tells us telnet was able to connect to the proxy, and telnet, curl was able to connect to the proxy, and the proxy actually made this request to the client, to the server, and the server returned the HTML web page. So the proxy made this request get localhost 9000 home.html and return the response at the bottom. So I could put some printf messages where the proxy is making a connection with the server, and this will become more clear, but I haven't done it. Right, so that's all you have to do. So you have to fire up a server, tiny web server that serves that adds two numbers and the image. You have to set it up. You have to write your proxy. You have to fire up your proxy, and then you have to use two debugging tools, telnet and curl, to make sure that your proxy is communicating with the server and it's caching requests, and it's able to handle multiple requests and serve them concurrently. And all the proper read-write logs that we will teach you, concurrency primitives that you will use to make sure that this cache is always in a consistent, its integrity is not destroyed by multiple clients trying to write to it. It's not the clients that write, it's the cache itself that writes something, but you want to make sure that those writes are not, right, they are properly synchronized. They are not, you're not destroying the contents due to concurrency. So there have been forward references to concurrency in this lecture. I think you have the basic idea from signal handlers and processes. We will start with concurrency in detail on Thursday and continue it in the next week or two. That's it. Bye.